Okay, today we're in transition in wrapping up Chapter 3 and then getting into Chapter 4. We're also going to finish up Fourier series, obviously, and then talk a little bit more about spectrograms. Not that we've talked about spectrograms in here at all, but you got introduced to the spectrogram last Friday if you worked the lab far enough. I don't know if you made note of the fact, but the homework this week is lagging out until Monday. Did anybody notice that? Okay. No one said anything. No one complained. So I figured you probably just said, "Oh, is this for real or what?" The reason why I lagged it out like that is I figured you're getting burned out with having to be prepared for a new lab, turn in a lab report, and turn in homework and prepare for a quiz all on Friday. True? It is pretty intense, I admit. There still is going to be a quiz, and you still start a new lab and still turn in another lab report, but the homework will be due on Monday, so that's 1/4 of the activity. And the lab that you're starting is a 2-week lab, so it's not going to be rushed up, and there's probably going to be sections out of that lab at the end that I'm going to delete and not have you do. I haven't decided exactly which part, but it's probably going to be the section on clarinet sounds. If you looked at the lab, you'll do the bell sounds, but you probably won't do the clarinet part. I'm going to talk a little bit about the homework, obviously, as we had to close out Chapter 3. And also, when we look at the example sheet, we'll talk about the quiz a little bit, what you can expect on the quiz. I've already posted up hints for the homework assignment, but I'll also take questions on that too, because what's going to come up now that the homework will be due on a Monday, you're going to say, "Oh, I didn't know what to do because it was the weekend." Right? I mean, there's always an excuse. There'll always be an excuse. And I'm okay with that because I do the same thing, right? The weekend comes and then you're recreating and you're not doing your homework, so it doesn't matter. There's always an excuse. So I do want to make sure that you can ask the questions that you want to ask. Are you guys listening? I thought I heard a second conversation. Does anybody want to tell me what it's all about? Because if it's important, I mean, we all ought to be hearing it. Okay, last time we went through one example of Fourier series. We went through the ideal square wave example. And just to back up a little bit, the tediousness of computing Fourier coefficients comes about when we have to jump in and do this Fourier integral. So what we were doing last time, and what we're going to do again today for another waveform, and you're going to play with it a little bit in one of the homework problems, is this, wrong function. Is having to do the analysis equation where you have to do that integration. So for the case of the square wave, it was pretty straightforward integration, but it's a little bit tedious to keep track of everything. So what we had with the square wave is we had to do a piecewise integration, and because the square wave was 1 during half its period and 0 during the other half of its period, it worked out that we just had to do one integral. And then we had to do some observing by plugging things in and looking at the fact that we had this annihilation going on here. When k was even, that numerator went to 0, and when k was odd, the numerator became 2. So that ultimately gave us Fourier coefficients that are non-zero only for k is odd, 1/2 when k is 0, and then 0 for all the even integers. And then we looked at the line spectra of that, plotted out using MATLAB, and then synthesis of the waveform using a finite number of sinusoids. This is something that I'm going to have you play with on the next homework assignment, the idea of synthesizing a waveform from its Fourier coefficients. But I'll give you the Fourier coefficients. You'll just have to have MATLAB make the pictures for you, just so you can get the feeling for how a finite representation works. Finite term representation of some waveform. Then we looked at this example of the frequency tripler, which was this block diagram here. I passed that circuit around. I'm going to have this demo running in the lab on Friday. So I'll get you introduced to the spectrum analyzer and the network analyzer, which will sweep the frequency response of the filter. And frequency response is not something that we've officially talked about yet, but we will be getting into that. Most of you, if I say frequency response, though, does anybody have a reaction if somebody says frequency response? What do you think that means?
Does something based on the frequency value.
Okay, does something. What could that something be?
Filter.
Okay, have an amplitude versus frequency is what we're going to move towards. You might think an easy example is in your stereo system, you have tone controls. You might just have bass and treble, but you might have a bunch of sliders and equalizer. So does anybody know what I'm talking about when I say an equalizer, where you have sliders that can adjust, like pass a certain band of frequencies and not pass others by bringing one slider up or pushing it down? That's what this bandpass filter in this example is like. The red passband is right in here, and that's like bringing up the gain over one band of frequencies and attenuating everything else in that neighborhood. So what the network analyzer can do that I'll have in the lab on Friday is it can take the filter portion of the frequency tripler that I passed around. Remember, the filter portion was the circuit elements that were the capacitors and the little inductors that had bands on them. That was a bandpass filter, and it can sweep that response versus frequency and show the amplitude or the gain versus frequency. And by studying that performance, we can see if that will suffice in this particular design application. In other words, will the filter pass the third harmonic and reject the first harmonic and the fifth harmonic and so on? And by analyzing in the time domain and using the spectrum analyzer, we'll see that the limiter converts the sine wave to the square wave good enough. When I say good enough, that square wave looks pretty ideal. It's got very sharp rise and fall times, or short rise and fall times. When it's done with the electronics that was on that board I passed around, it's not going to be so perfect. It's going to look more like just a clipped version of the sine wave. So it's not going to have really fast rise and fall times. Is that believable? I mean, if the diode is doing what I described, namely clipping the waveform, I'd have to have a high gain amplifier as well as the limiter. But I talked about comparators, and that's something you learn about in electronics. Then it can apply gain plus the clipping action. But here, it's going to look like a clipped sinusoid, but still we'll see that because it's done nearly symmetrically, there'll be a good array of harmonics that will get generated. But guess what? Even though we've analyzed the square wave, we could analyze the clipped sinusoid by finding the Fourier coefficients and verify that it would have a similar distribution of harmonics in it. And that's the beauty of the Fourier analysis. If you can have a piecewise description of that clipped sinusoid, you can plug it into that analysis equation and solve for the Fourier coefficients. Now, you're right in thinking that's not going to be a whole lot of fun to do that integral. But it could be done numerically. It can be done in computer simulation. And if you really had to do it, you could do it an exact closed form with the help of some integration tables. I'm convinced of that. Integration tables, you can just do just about anything if you really set your mind to it. And if you come up and ask me about that in my office, I'll show you some of the thick books of integration tables that I have in my office from a long time ago when I was in graduate school. Nowadays, you'd probably say I'll use Wolfram Alpha or Wolfram or something, but these books have been around a long time, but they still have, in some senses, maybe bigger catalogs than any software has got. I'm not positive of that, though, because copyrights eventually expire, so maybe the whole book is on the internet, for all I know at this point. But now we're going to move on and take a look at another waveform, and then this will be the springboard into the waveform that's in the homework. So this is another classical waveform called the triangle wave. Generators that are sitting on the lab benches in the lab that are called function generators traditionally produce a variety of waveform types, and they generally produce square waves, triangle waves, sawtooth waves, which is the waveform that's in the homework, and pulse trains. Those are four classical types of waveforms. I said three. I meant three. However many I listed off. 3 types, 4 types, whatever. There's also waveform generators called arbitrary waveform generators that you can program in custom waveforms, and wave shapes of different types show up in different applications, so that's why generators exist. But triangle and square are kind of classical beyond the basic sinusoid. So the triangle wave, in reality, the triangle wave comes about by integrating the square wave, if you can believe that. Because if you got a constant value and you integrate it for a period, it's going to ramp up to a bigger value. So actually you'll learn later that, again in another course, but not so much in this class, if you were to send the square wave through an integrator, it would come out as a triangle wave. So what happens if you send a triangle wave through a differentiator function? It comes out as a square wave, and that those are functional building blocks or systems. So an integrator can be a system, just like the filters we were talking about. It's a type of filter, and just a pure integrator. But not thinking so much about that, just look at what is the form of the triangle wave. First, we have to start off either with the picture of it and have the piecewise description, or vice versa. I could suppose that somebody said, this is a waveform we'd like to test with, a triangle wave. So what's the piecewise description? Remember, you had a homework assignment. We talked about that in the last chapter, getting a piecewise description. So in this case, if we went backwards, we'd see that on the interval from 0 to t naught over 2, this is our mathematical description, 2t over t naught. And then we have the opposite slope with an offset due to the intercept point being moved of the line for the next interval. So we have to describe what's going on in that interval. And all we need for our Fourier analysis is the piecewise description on one period, and then we're good to go. So this description over here is only valid on the interval 0 to t naught. But once we have a description that's good on one period, we can do everything we need to do, because we can just sort of replicate or rubber stamp that description over and over again to make a periodic signal. So that's the mathematical description. Now plugging into the Fourier integral for getting the Fourier coefficients. We'll start with the easy part. The easy part is just finding A0. So to do A0, we just need to plug in the x of t and integrate over one period and then normalize by the period. So for this waveform, again, you can do that by inspection, right? Because it's a triangle, you can find the area under the triangle. So it's 1/2 the base times the height, and that gives you the 1/2. What happens if the triangle wave happens to be sitting about 0? So another type of triangle wave would be one that would sit like that. So it goes between 0 and, say, +1 and -1. What's A0 for that waveform going to be?
0.
Okay. What's the reasoning behind that?
Half's above and half's below.
Okay. So the areas cancel. Okay. So you can see something kind of intuitive about if you take a waveform and just bias it up or down by a constant, you can control its A0 value. Do you think biasing the waveform up and down changes the other Fourier coefficients? Like the harmonics at the fundamental and the second, third, fourth, and fifth? You say no. What about anybody else? Stand firm in your thinking. So does anybody think it does?
Well, I don't see how that's a 0 area.
Well, the way I drew it is probably not a 0 area because I didn't draw it perfectly, but if I draw one period, which would be that, okay? Then we're talking about that area, canceling that area.
I was looking at something totally different.
But now the question we're talking about right now is if I just pick an arbitrary bias value, and see in electronics it's very easy to take a waveform and send it through something called a level shifter, which just takes the waveform and electronically applies a bias, so it just raises and lowers its DC offset. Will that alter any of the other Fourier coefficients?
Those are based on harmonics, aren't they? So that's
Yeah.
based on frequency.
Okay, you're right. I mean, think back to the projection idea too. Remember when we were talking about the IJK unit vectors in the corner there behind me? The Fourier coefficients are like the projections of the signal onto the different basis functions, or the functions that make up the waveform. And the functions in this case, in the abstract vector space sense, are DC, first harmonic, second harmonic, third harmonic, or fourth harmonic. So just raising and lowering the waveform by constant is only altering the projection onto the DC component. It has nothing to do with the wiggliness of the waveform, is another way of thinking of it. So it doesn't alter the harmonic content. So our ears wouldn't hear any difference. Now, if we were sending it through an audio amplifier system that was DC coupled and the waveform moved up and down, the DC bias changed on that waveform, and it was DC coupled into your audio power amplifier, and you went to look at your speaker cone. Does everybody know what a speaker cone looks like? If you tear the grill off your speaker, you see this paper cone. Have you ever looked inside and torn one of those apart and wondered how they work? There's a coil of wire that's at the base of that cone, and it's generally got a magnet around it. So when current flows through that wire and then the permanent magnet is there, the AC current flows through to the waveform current, it interacts with the magnet and it produces a force that makes the cone either push out or suck in, so it moves back and forth according to the direction of the current flow, because there's a resisting effect on the constant magnetic field and then the alternating magnetic field from or current flow through the conductor. So on a real live speaker, if you put DC into it, it abides. It'll either push the cone out or pull it in. So if you put a DC bias on your waveform, you would force your speaker cone to either move out or pull in, and it only has so much travel that it can go over before it bangs into something on the backside, or I guess too much current goes through it and it burns up. I mean, various things happen when speakers go bad, but the DC would, in general, could destroy it, especially if it pulled it back too hard Generally, there's some mechanical structure back there, and if it crashes into that on the back of the cone itself, it will damage it, and then it will start rubbing, and then it won't sound very good. I bet some of you have blown out speakers by overdriving them, and then they sound kind of awful later. Has anybody ever done that? They don't sound the same after you've done something harsh to them. My brother built really high-power audio amplifiers when he was in high school because he had a DJ service, and he would crank his audio stuff up really, really loud for the dances he played at. And he would have to realign his speaker cones because he bought custom stuff that he could actually tear apart and rebuild if he damaged them. So he'd get in there and he'd push it back and forth and listen. Is it rubbing? Is the cone rubbing against the magnets? If it got out of alignment, he'd tear it apart and realign it. But nowadays, I think you throw it away if you damage it. Okay, I got sidetracked there, but the idea would be that that bias would not contribute to the audio because it's just a steady value. Okay, so now when we move down to do the remaining terms, we have a piecewise integration just like we did before with the square wave, except now we have activity on both halves, so we're going to have to break the integral up into two pieces. So do the first half period with the upslope and the second half period with the downslope. So that's these two pieces right here. And there's no immediate symmetry that you can put to bear on this problem unless you start doing some finagling with the integrals and the limits and changing variables and so on. Right? I mean, there is symmetry, but it's not immediately obvious. It might actually be easier, and I didn't do it this way in the problem, but you could do it this way. We're integrating from 0 to t naught. If we wanted to, for convenience sake, if we thought it was better and made our life easier from an integration standpoint, we could slide over here and we could do this as one integral and this as another integral. What's an advantage of doing it that way that you can see? Maybe some cancellation, but what's a particular advantage? What about the piecewise description? For both pieces there has the advantage that it goes through the origin, right? I don't know, I like that better myself. Does anybody else see? I mean, the first integral here is not too bad, but see, this one is messier because you've got the t naught minus t. See what I'm getting at? So you're going to do the math someday when you have one of the other follow-on classes to this one, and just be wise. I mean, try to make your life easy. You don't have to be superhero and say, I'm going to take the messiest setup. You want to be smart. You want to pick the easiest way of going about this. So the way we'd integrate the t e to the minus at, which is basically what we have here, or t e to the minus, or basically x e to the ax is what we have in here. I mean, that's the hardest part of the integral, that we have a t and an e to the t. I didn't get the t circled, but... So that requires integration by parts, or as I did here, I looked it up in a handbook and just got the integral for that x e to the ax, and then you just put your limits into it and you've got it. So how many applications of this integral formula do we need in this to do this equation 338? I mean, how many times do we have to use that formula? I see it once right there, and then I see it when we have this term from the second integral, right? This term right here is the constant case, so that's like what we did for the square wave. We wouldn't have to use the integration by parts formula. That one we can do straight away. But the way I see it, there's basically three integrals to be done there, those three different pieces, if you just dive straight in and don't try to break it down. Well, when I wrote these notes up in 2006, I decided to let Mathematica take a crack at it. So I told Mathematica to do it, and you could do Mathematica different routes, but I just broke it up into the two pieces, called it I1 and I2, and then I said add I1 to I2, and then I said do a full simplify on it, and this is what it gave me. And in Mathematica, this funny looking I, I'm kind of blowing it up there, that is equivalent to sort of a double-sided J that they also have in their notation, but when you're solving a problem and you're getting a complex solution, it always defaults to I instead of J. So that's just the square root of -1. But right away we can see that Mathematica, one of the things I would have preferred to do is have it say cosine of k pi is really just -1 to the k, like we saw before, right? So I make that substitution, and then I see that substitution also applies over here. E to the -I k pi is also -1 to the k. So I work those in down below in this line right here. And then I say, okay, I've got, in the square brackets here, I've got something going on just like I did before. I have this addition and subtraction going on. So when k is odd, I'm going to get the combining of those two inner terms, and when k is even, I'm going to get the annihilation. So again, I've got just the odd terms coming out. The even terms go to 0. And then I've got a -1 to the k out in front of all of that. And let's see. -1 to the k out in front of all that doesn't cause me a bit of harm though, right? Because if I'm only going to evaluate this when k is odd, what does this term always evaluate to? -1. And then the inner term in square brackets has a -1 that I can factor out of it. So those come out together. And that's why I've got a +2 sitting over there. The brain is more powerful than the computer, I think, at finalizing these symbolic solutions. So we've got 2 over k squared pi squared, 1/2 for the DC value and 0 for the even harmonics. So I can plot the spectra again, and the square wave had harmonics that dropped off at 1 over k. That was the proportionality constant. Triangle wave, they drop off at 1 over k squared. So they both have just the odd harmonics, but the smoothness of the triangle wave that has, triangle type shapes rather than the sharp edges of the square wave where it jumps up and jumps down. The difference is that the harmonics roll off faster. And if you're a person that likes to listen to music really loud, where you distort your audio system, you know what the tendency is when a signal is getting clipped or just pushed out of an amplifier where it's distorting, it produces more what's called harmonic distortion. So the harmonic content for a given stretch of music is going to have more overtones associated with it just because of that limiting action. So the square wave you could think of as a highly limited version of the triangle wave, or the differentiated version of the triangle wave. So its harmonics roll off more slowly. It has a harsher sound when you listen to it. Triangle wave sounds a little bit more mellow because the harmonics are falling off faster. Sine wave would be the cleanest sounding because it just has one spectral line. It has a spectral line at F0, and of course minus F0. It's just a single tone. So the way I think of it is the smoothness of the waveform means the harmonics fall off faster than a waveform that has sharp edges in it. And this is pretty much true of all types of waveforms. If there are no sharp rises and falls in them, then the harmonic content drops faster than compared to one that has sharp jumps in it. And an aspect of reconstruction, remember when we tried to reconstruct a square wave from just a few of its harmonics, it had all that ringing on the flat spots of the square wave. And that was because at the discontinuity, or where the square wave is jumping from minus to plus 1 or 0 to 1, the Fourier series doesn't converge very well. But because of the smoothness of the triangle wave, you can see that with just a few harmonics, like 3, 7, up to 15, notice how nicely it's converging because of the smoothness of the waveform. That's just a fact of the underlying waveform that we're approximating with a finite number of coefficients is got an easier job because of the smoothness of the waveform. You know, the harmonics get weaker more rapidly, so it just converges better. Does that seem intuitively reasonable? So another way of turning that around is if you have a finite amount of bandwidth to send your signal in other words, like through a telephone or a cell phone, you only have up to 4 kilohertz to send your audio content through. It'd be easier to send a triangle wave through a finite or band-limited system than a square wave, because the square wave harmonics are going to get thrown away by the natural filtering action in getting it ready to go out over the band-limited audio channel, whereas the triangle wave, not as much of the waveform is going to get thrown out in that band-limiting action, so it will sound better than the square wave would in terms of its original character.
I have a question.
Yeah?
When you integrate the triangle, does that give you a sine function?
No. What do you think? What happens when you integrate a straight line or a ramp?
It give you a quadratic.
Yeah, so it's parabolic in shape.
I didn't know if that
Yeah.
looked like a sine at all.
No. It's another waveform, though. Maybe it's one for the quiz or something like that. That's okay. I mean, what should it look like? If you think about what it's going to do, it's going to go quadratic, like you said. So it would go something like that, I think. There's all kinds of wave shapes. Remember the Shams Outline Mathematical Handbook I brought in? In the back of that book, there's a section on Fourier series coefficients, and there's a bunch of tables for the coefficients, and then there's waveform pictures next to each of the coefficient sets. So they've got all kinds of different wave shapes analyzed in there. It's like I said, it's a cookbook or a lookup table. A lot of those wave shapes aren't things that we see in signal processing. You know, I guess you'd say they don't occur in nature, you might say. But in reality, you know, a lot of things would occur in nature. If you're trying to look at electrocardiogram, getting your heart, you know, going through its cycle, that's a pretty complex looking waveform. It doesn't have nice linear slope. It's piecewise something or another, but it's got, you know, a variety of different piecewise shapes that make up the heartbeat, and that's only if it's regular. I mean, if it could change from beat to beat, but assuming it's an idealized carbon copy every cycle. So we've been talking about convergence. This is just some of the stuff that's in the book on convergence, basically showing that convergence is very poor in a square wave at the point where it jumps. That's all this is saying. That's why it spikes up every now and then as you go across the time axis. That's where the error gets large because it can't approximate at the point of discontinuity. The next little bit here at the end of this chapter is time frequency spectrum, and that's the spectrogram. We're going to take a look at that. I'm just thinking to myself, what order do I want to do things in? We'll go do this for a while, then we'll jump back and look at the homework problems. The spectrogram you got introduced to in the lab, and some of you maybe didn't run it yet. Has everybody, how many people have played with the spectrogram already since last Friday? So about half of you. Pretty nice function, isn't it? I mean, it gives you a time frequency domain view of a waveform. There's a lab that we're not doing that relates to music, and that's why this stuff with the keyboard and instrumentation is in here. Maybe some of you were hoping we'd do that lab. But when I first started teaching the class, I got feedback from the instructors ahead of me that students found the lab involving writing out music was very tedious and just challenging. Maybe some of you would like writing out music and playing it. But I decided to go with the bell sounds instead, so that's sort of like the substitute lab. You will do a lab where you're going to generate touch tones and then decode touch tones. That's kind of the capstone lab at the end of the semester. So you're going to generate the tone pairs that come when you hit the keypad on a phone, and then you're going to synthesize those so you'll be able to hear you dial a phone number, dwelling so many seconds or fractions of a second on each note pair. You know, every time you press the keyboard on a touchtone pad, you have a row frequency and a column frequency. So you'll generate those. They'll go across a channel, a quote channel, as if they're going over a telephone line. And then you're going to be building a digital filter bank that will decode the touchtone pairs of frequencies and then decode it back into a telephone number. So you're going to build an encoder and a decoder in software, in MATLAB. So you will do some types of synthesis with that. But spectrogram in MATLAB, it's actually spectrogram. That's the full spelling of the word. So the function that I actually still find the best is this original one that was in the signal processing toolbox, which is called specgram. Get my finger on the button. Does anybody know why it's not spectrogram? This is a historical point of trivia, I guess. I told somebody last Friday, I think.
Had to do with DOS.
Yeah, if you have worked in the DOS world, which I did when MATLAB first came out, DOS only allowed file names with 7 characters for the first name and then a dot and then 3 characters for what you might call the last name. So it was the 7.3 file naming convention. So all file names had to be restricted, and this one I guess is 8. So there must have been something else that was eliminated in here. I don't know. At any rate, they had it truncated, I think, to fit the DOS, or maybe it was 8.3.
That makes sense.
It's probably 8.3. See, it's been so long now that I can't even remember. That was in the era of the big 5 and 1/4-inch floppies and all that stuff. I mean, that stuff all went together. So spectrogram is a newer one, and it's a little bit more exotic, but specgram has got a nice, simple interface, and it's still supported. It's one that the MathWorks, I think, is trying to eventually retire. So I think if you try to type help on spectrogram, you don't get any help because it will say it's a deprecated function. Has anybody ever run into that yet in MATLAB? The term they use is deprecated, which is an interesting name in itself, but means it's a function that in the next iteration they can pull the plug on it, and you've been warned for numerous, updates that this function may go away, so you should be converting to the newer function. But I still like using it. You input the signal that you want to do the spectrogram of, you put in the window length, and then you put in the sampling rate for the display. How many samples per second was put into the waveform. Typical values that work well in this class are, say, a low of 256 and a high of 1024 per record or sub-record. In the Bell Tones lab, you're going to be doing some FM experiments, and I think you'll do those already this Friday, where these two numbers actually work better. Basically, what the record length or window length does is you can visualize your data as being this long record of data. So you break it up into n segment long chunks, and you're computing the spectral estimate using something called the fast Fourier transform on each one of those chunks. The longer the chunk is that you can process, you get better resolution, but if the spectrum is changing in that interval, then you get a blurring effect. So if it's changing rapidly, you're better off going with a shorter length window so that you can capture more precisely what's gone on in that short little interval if it's changing rapidly. So there's a trade-off in there. But like I said, you want to play with that value and kind of get the best picture. So an example that's in here is just playing a scale in MATLAB and then doing a spectrogram of it. So you can see what happens when you all of a sudden jump from one frequency to the next, just instantaneously change frequencies as if you're hitting the keys on a piano. The spectrogram, if it captures a record of n points and it straddles part of the first frequency with the next frequency, it ends up getting this splattering effect, and that's what all this garbage is in here. It's not really that the note is spreading its energy over all those frequencies. It's just that the algorithm itself is getting confused because you've got a record of data, n points long, that has some from each tone in it, and it gets a transient, a jump in frequency, so it spreads out the spectrum at that point. A nice application of using the spectrogram to see what's going on is the chirp signals that you worked with last Friday. So we already talked about the linear chirp, and this analysis that I put in here is basically the analysis. Remember, this equation is what you were implementing in your MATLAB code last week, and this instantaneous frequency was the equation that was key to figuring out how to come up with a value for mu and f naught for a given start frequency and a given stop frequency. You've got another example of that in the homework for this week too. This is just a strips plot of a chirp that's going up and up chirping, and then a spectrogram. This comes out nice because the frequency is just taking tiny little steps over each sub-record in the spectrogram processor, so it looks pretty clean. It looks pretty dark and solid along the slope where the frequency is linearly ramping up from 100 to 1000. What I was going to do now is just show you some other applications of the spectrogram on a more complex signal. I loaded up in MATLAB the bat sounds that I gave you a taste of last time. And this was a senior design project, so these sounds were captured when I worked on this project at the zoo. What the zoo wanted to do with their bat cave, and they don't have the bat cave the way they once had it, bats echolocate with ultrasonic sound emissions. You probably knew that. You know that some animals can screech above our human hearing, and they echolocate just like radar is used to figure out where objects are around us electronically. So bats do it, and they hear their echoes in return, and then they use that to help decide how to guide their flight, to either get to the food or avoid an obstacle, or maybe avoid another bat, I guess. So in the bat cave, what they wanted us to do was put in an ultrasonic microphone array, because we didn't know exactly what frequencies the bats were chirping at, or at least we decided to take an approach where we just put in an array of ultrasonic sensors that you'd find in a burglar alarm that they use in buildings at public, private buildings, homes, etc. So it could recover the acoustical sounds at these ultrasound frequencies around 30, 40, 50 kilohertz. And then we wanted to be able to display them on an oscilloscope, so that was no problem. amplifying and then directly displaying, but we wanted also to be able to hear them. They wanted to have in the kiosk outside the bat cave a speaker that would translate, or as I described it last time, pitch shift the bat sounds from the ultrasound to something audible. So that was part of the electronic design, was to put in something that would translate the bat frequencies down to an audible range. And in the process of doing that, I captured some records of data on analog tape using a cassette player at that time. And that's what I've got processed out here. So I've loaded these into MATLAB, and the way you'd load them into MATLAB is if you have a WAV file, I just double click on it when I'm in the MATLAB environment, and it says, oh, I know what a WAV file is. I'll import it for you. I'll bring it in as a long vector of data, and I'll bring in the sampling rate, which was encoded into the WAV file. So I did that here, brought in both records, one that I called Bats and Bats Slow, and the sampling rate was 44.1 kilosamples per second, which is the CD rate. So Bats is, as we're going to listen to it, the bats that were at the bat cave or the zoo were fruit bats from South America, and fruit bats eat fruit. So when they fed them, they would hang pieces of cantaloupe in the bat cave by a string, and the bats would go crazy. They were just swarming around, all trying to get the cantaloupe. So they were having to echolocate a lot. And that's what this first sound is going to be. Actually, I should probably slow that down, so I'll take it down to 22.025, so it plays slower. Or 22.050, I mean. So I don't know exactly what they're doing, but they were definitely flying around. I mean, it was in a darkened room. There was a dim light. All we could see is the shadows of these dark objects just, swarming around. And the bat cave was an area that was darkened, so you went into this room and you were already in a dark area, your eyes adjusted, and then the idea was you were going to try to see the bats, but then this system allowed you to know that they were active if they were echolocating. So a second sound is the bat slow sound, and this one I processed down by slowing it down and then homing in on things a little bit more. So I'll play it at the original recording speed, which was slowed down by a factor of 4 from the other recording. And this one is the most interesting one, because this was just an isolated bat flying across the cave. There wasn't any food in there. We just happened to capture it when we were down there. And I have some suspicions about what was going on. The bat was either going after a target or it was just echolocating off the wall, but it let out 3 chirps. I mean, just play that again. Pretty distinctive, right? There's what they look like when you plot out the time waveform. So I could zoom in on that, and there's chirps in there where it's chirping up in frequency. As a matter of fact, I can go to the spectrogram of that. And then if I zoom in on it, down at the lower frequencies, these pieces up in here are images from the downsampling. It's something, when you downsample and you don't filter enough, you'll get images. So these are mirror images here, here, and here. These are the dominant pitches we're hearing, though. So the first chirp is this linear chirp right in here that goes up to about 1,000 hertz. And then another one chirps up to 1,000, and then that one chirps up to 1,002. But what do you notice about them? They're, thinner. They're chirping faster is what I'd call it. The chirp is quicker. And from radar theory, if you spread the energy out over a longer period of time, you can get a more solid return because there's more energy being spent in transmitting the radar pulse at a target to get energy back to know that it's there. But because it's taking longer to send the information out, the resolution is not as good. If you can chirp a slow little, a more rapid chirp, then you can get finer detail about finer resolution. Does that make sense? What I'm trying to do is, I'm not a biologist. I didn't go talk to a biologist after I did this. I just looked on the internet and did a little bit of studying. My reasoning is the bat is an intelligent echolocator, just like a military radar might home in on a target. The bat chirped for a long time, put out a lot of energy and got a return. And then it chirped again with a faster chirp to get finer detail, and then it chirped one more time to get even finer detail yet. That's my theory. Does that sound too far-fetched? I believe bats are smart. If they can't see, they have to figure out where they're at, and they don't have bodies built of iron, so if they crash, they probably get hurt. But the spectrogram reveals that, or at least makes that a plausible explanation. Is anybody interested? I guess I could go to a biology person and say, what do you think? I don't know if there's anybody here that studies them, but... So that's my demo of the bat sounds. It was a cool project. Have any of you ever been to Carlsbad Caverns? You've gone in that entry. There's an entryway where it spirals down, and if you're there at the right time, there's lots of bats that fly in and out of that big hole in the ground. I've never been there when the bats are going in or out, but you can see the signs of the bats when you're there, though. It's a pretty neat cave to go into if you like caves. And I like caves like that. I'm not into the spelunking where you got to go in the slimy, tight places and get claustrophobic and, I don't know, never come back again. Does anybody have any questions? So what we've just learned in a summary is that we've gone through how signals composed of sinusoids were the central theme of the chapter, and they have a line spectra. And then we got into periodic signals in general that would have a Fourier series representation, in other words, decomposed into sinusoids of different amplitudes and phases. And lastly, tools for looking at waveforms could be, besides the spectrum, it can be the spectrogram, which gives us an indication of how the spectrum is actually changing over time by slicing it up into subrecords and getting the spectrum of each subrecord. I believe spectrograms are also used by the National Security Agency a lot when intercepting signals and speech waveforms from individuals. Think of targets that the U.S. is looking for that they would like to find somebody. Osama bin Laden, for example, he's somebody we've been looking for a long time, supposedly. So his spectrogram has probably been fingerprinted by some recording, and then you could use a template to try to isolate certain parts. You can do that for anybody, spectrogram matching, and then ID somebody based on that, because that's a fingerprint. Unless you modify your vocal cords or something, you've got something that's probably not as good as DNA, but something that's helpful. Okay, in the homework assignment, you've got the first problem has got this sawtooth in it. So finding the A0 coefficient should be pretty straightforward. what I'm challenging you to do is find the A1 coefficient. Oops. So that's going to require an integral. It's not exceedingly difficult because to find the Fourier coefficients here requires how many integrals to do? Just one, right? So you ought to be able to find that pretty readily. As a matter of fact, if you could challenge yourself and just find it for all values of k or n, because it'll extend pretty readily from that. But all I'm asking you to do is find A1, which is setting k equal to 1 in the integrand. Second problem is a pulse train, and I'm not asking you to find all the Fourier coefficients for this pulse train, but I am asking you to find A0 for the pulse train as defined, and then look at a modified signal, y is equal to a plus x of t. And in the modified signal, the idea is we want to choose the value of a, which is the bias that's going to raise and lower the signal, so that the average value is 0. That's just basically a waveform design problem. Once you know what A0 is for the unbiased signal, x of t, then you can come up with the value for a to make the A0 for the y of t be equal to 0, just by biasing it accordingly, and then sketch the waveform. I can't really say a whole lot about it, because if I do, the answer will be right there. It just pretty much is right there in front of you. Problem number 3 is just like one of the problems you did in the lab already, is that you don't have to do a MATLAB simulation, but it's just setting it up to get a signal that chirps from 2,000 down to 50 hertz in 2 seconds. Problem number 4, which is continued here on the second page, is a little bit more exotic, but I've given this problem before, and I used to have a bonus part, and the bonus part was to prove this, but I decided not to even offer that this semester because most people never took me up on the offer to get bonus points. I will have some homeworks that will have bonus points in them, though, at some point. But you get to use this property, and this is an important Fourier series property. That is, if you take a waveform x of t and you time shift it, amplitude scale it, and then bias it, the Fourier coefficients of the original waveform, which would be the a sub k's, so the a sub k's correspond to the x of t. Then the question is, what do the b sub k's look like in terms of the a sub k set? So the theorem says that bk is equal to a plus b times a0 at k is equal to 0, and then bk is equal to b times ak e to the minus j 2 pi t naught times k little t naught, where little t naught is the time shift of the square wave. So in particular, starting from the square wave that was defined in the book, and the one we did the example on last time, square wave that comes up here, goes down, it was 0, 1, I believe. How can we, once we know the Fourier coefficients for that waveform, so we have the a sub k's for this square wave, which we already did, what are the Fourier coefficients for this new waveform x of t? I think in the book this was called s of t for square wave. So you don't have to start over from scratch and compute the Fourier coefficients all over again. Instead, you can use this theorem to get the new coefficient set in terms of the old coefficient set. Sound reasonable? Time saver. That's what theorems in Fourier analysis are all about, and you'll get introduced to a lot more Fourier theorems in the next 2 semesters, but we're going to be playing with some Fourier theorems and Z transform theorems later in this course too. So we're going to have two types of transforms we're going to be looking at, primarily the Z transform, but a little bit of Fourier analysis too, only in the discrete time domain. So I think these problems are pretty straightforward. But I did put up a hints page that has some of the verbiage that I just spoke in it. So now, jumping back over to our worksheet from last time, I think we had worked the second part of the example pretty good. Does anybody have any questions or anything they want to add? Basically, I can throw any periodic waveform at you in plot form or in piecewise form, and you should be able to find out what A0 is. So as a side little example, suppose the waveform had something wacky in it, just creatively wacky. I'm saying that goes up like that. To something like that. Come on. Trying to get the right colors here. I'm getting confused. Suppose I made that parabolic in shape. You could do that, right? Because you can integrate a polynomial. Does that seem too cruel? I think it's pretty straightforward, actually. So, I mean, you could even bump into something like that. So be on guard. This is a candidate type of problem. I mean, in general, finding A0 from a waveform or piecewise description is something that I'm going to expose you to on the quiz on Friday. But it may also, rather than being something like this or two small problems, it could also be the first type of problem that's in here, where you're just getting the Fourier coefficients directly by inspection. So if you looked at this waveform and we wanted to get the Fourier coefficients rather than just A0, well, first off, we could look at this and say, suppose all I cared about was A0. What would A0 be for this waveform? But I heard one person give an answer. What do you think? Well, the average value, remember, A0 is just the average value of the waveform. So it's going to be 1 over T0 times the integral of x of t dt as you integrate from 0 to t naught. So plug that whole waveform in there and you think I got a mess, but what did we talk about last time? When you integrate cosine waves over a period or multiple periods, what happens? What do they integrate to? They always integrate out to 0, right? The average value is 0. Now you're saying, but I don't know what's going on here yet. I have to find out what the period is. So actually the first thing before you could even set this up is you'd have to say, what is the period? So before you find out what the period is, you'd probably say, what's the fundamental frequency? That'd be the starting point. So what is the fundamental frequency here?
500.
Okay, so you say it's 500. If it wasn't periodic, then you couldn't even talk about Fourier coefficients. So the Fourier series only applies to periodic signals. So I won't ask you a trick question where I'll say find A0 and it's not a periodic signal. So that's got to be a given. But you do need to know what F naught is, and then that implies that T naught is 1 over 500. So now we'll integrate over multiple cycles. So we'll be integrating over one cycle of this as we integrate from 0 to t naught. And how many cycles of that one? 10 cycles, right? It still integrates to 0. So the only thing that's going to come out with that integration is the 5 integrated over 0 to t naught. So that will bring in, 1 over t naught. And then there'll be a t naught times 5, which is just 5. So the DC value, or the average value of that signal, is just 5. Now what other Fourier coefficients are going to be in here? Okay, so a plus and minus 1 is in here, and a plus and minus 10, because we have the fundamental at 500 and then the 10th harmonic at 5,000. So to get Fourier coefficients from a cosine wave, it just has two coefficients, right? The plus and the minus, and that's from the inverse Euler identity. So the a plus and minus 1, by inspection, what is that going to be? Just expand this out, right? So it's the 16 over 2 it's going to be minus plus, actually, from the Euler identity, because there's a minus sign in here. Does that make sense from Euler's identity, inverse identity? Just breaking it into two complex sinusoids and then factoring out the magnitude and the phase, and that's the Fourier coefficient. Then the next one, because it's a sine, we have to convert this first to a cosine, so we need to subtract a minus pi over 2 in here. And then that nets us out what? Minus 3 pi over 8 is the net out of that. So here we would have a 10 over 2, right, because we divide the amplitude by 2. And then the phase on this guy is that it's going to be the minus and plus j 3 pi over 8. Admittedly, I didn't spend as much time on this, and we are just about out of time. I'm still going to jump to do one other thing. Questions? You're seeing a lot. Hopefully, you're seeing a lot of things are kind of repetitive. They just kind of are taken in a different context, but we keep kind of doing some of the same things, and that's a good thing, right? You just have to recognize the context, but the math is all getting to be kind of more familiar to you. Just like MATLAB functions and things should start to be more familiar. There's going to be twists and angles, but there are some things that are kind of should be coalescing some more. I'm going to jump a little bit and look at sampling and aliasing. The only reason why I want to do this is because some of you are going to push hard on Friday. I know it's so because it's been proven to me already. You're going to get to a point where you're going to be puzzled about something that's due to aliasing. Aliasing is the idea, and we'll start on this on Monday, but if you drop way down here, I've got a definition of alias from the dictionary. A false or assumed identity, a spy operating under an alias. Computing, an alias as in a file name alias. That's, for those first two are no good for us. Third one, though, telecommunications. Each of a set of signal frequencies that when sampled at a given uniform rate would give the same set of sampled values and thus might be incorrectly substituted for another when reconstructing the original signal. That's what we study in this chapter, is that part of the definition. And probably, there's a lot of math. We'll be looking at the math. It's not hard math. It's just, this has got some conceptualization stuff. So I've got some pictures There's a picture on the website that's buried in there of these folded frequency axes, but there's one little example that's going to ring true when you do this in the lab. Suppose we're sampling at 2,000 samples per second. A property of the sampling theory is we have to sample at greater than twice the highest frequency, otherwise we get what's called aliasing. So you're going to do an experiment in the lab where you're going to create a linear chirp, and the chirp is supposed to chirp from 0 up to 2,500. But instead, because you're only sampling at 2,000 samples per second, as soon as you get to 1,000 samples per second, the aliasing ends up folding the frequency so that instead of going upwards, it now starts going downwards. And when it hits down at 0, it's still going to fold again, and it's going to go back up again. We'll be talking about the mathematics behind that, but you're going to observe that. So it's the folding frequency that counts, and like I pointed out, there's this little accordion and there's another accordion that I'll be talking about, another view of the same thing on a different axis in the accordion, but you go up higher in frequency and you'll jump across and pick up your alias. I don't have time to go into the details, but that's a concept, a new concept that you're going to have to get your brain wrapped around, but once you get it, you'll feel really comfortable with it, and you're going to be listening to it on Friday probably, so hearing will be confusing, but then you'll have this explanation of aliasing to explain what's going on. There's one other thing I was going to mention, I know I'm out of time, is one student came to me with a question on the current lab, the one you're finishing up on, and it has to do with writing this function called beat and how you load it into BeatCon. And I figured out what was going on after the visit to my office, but when you run this function BeatCon, and I don't think I can even run it unless I try to squish it on my little screen. When you say use external beat, what this GUI is doing is these sliders, amplitude A, B, frequency, duration, and so on, are going in and poking their values into your own custom function. That's what it's doing. I don't know if anybody got confused about that, because that part of the lab was a little bit vague. You can either go off on a tangent and never come back, but it's taking control of your own function, but it seems so subtle. The only way you can really prove it would be to go down here and do like I did and put a 2 times A in there and see, yeah, it's actually using my function rather than the one interior to the GUI itself. It's kind of, I think it's kind of dorky, actually. To me, it's like, why bother? But they just wanted you to get another exposure to some aspect of MATLAB. So if you didn't figure that out and you just plotted it directly, because that's what I told one student to do, plotted it in MATLAB, that's fine by me too. And I talked with Kyle about it, and he's aware of that fact. Okay.